Hello everyone, I'm Dr. Jyoti Mandala. Welcome you all to the video lecture series on the course Operating Systems. In this lecture, let us understand about how the solution to the dining philosopher's problem has been given using semaphores. In our last two videos, we have understood two more problems where the solution to the producer-consumer problem and readers-writers problem has been given using semaphores. I hope you all have gone through that video and understood how it has been solved. In this lecture, we will see this problem. So before going to the solution, let us understand what actually this problem is. Okay, so let us consider there is a round table, and on that round table, let us consider this is the table that has been considered. And in this is a dining table where on this dining table, let us consider five philosophers are there. P0, P1, P2, P3, P4. All these philosophers are here to perform two things only. What are the two things? They need to perform eat operation, and the other one is if they are not eating, they will perform the think operation. So let us place those philosophers first. Let us consider this is the first philosopher. So let us consider this is the philosopher 1, philosopher P0, and then P1, P2, P3, and finally one more last philosopher P4. Alright, so let us name these philosophers. Let us call this philosopher as P0 and this philosopher as P1, and this is P2, P3, and P4. Four philosophers are there. And in the middle of this, we let us place some food also for them. So here we have rice. Let us consider. Now, whenever they want to have this rice, each philosopher they will be using chopsticks to have this rice. So the chopsticks are placed like this, where the chopsticks are placed in this fashion. Here one chopstick, here one chopstick, here one chopstick, here one chopstick, and one more here. So total of five chopsticks are there. So whenever a philosopher wants to consume the food, to eat the food, they need two chopsticks, one from the left side and one from the right side. And using these two chopsticks, a philosopher will eat the rice. Okay, so let us name these chopsticks also. So let us call this chopstick as C0, this one as C1, and this one as C2, this is C3, and finally C4. So understand, we are having five philosophers and we are having five chopsticks. Now the work of the philosopher is to eat and think only. Two works only the philosopher will be doing. What are the two works? Eat and think. So whenever the philosopher is eating, he will not do thinking. If he is not thinking, he will eat. If he is eating, he will not think. Any one of these two works will be doing. The philosopher will be doing. Okay. All right. Now, the condition here is whenever a philosopher wants to eat, let us consider a philosopher P0. If a philosopher P0 wants to eat, he needs to have two chopsticks. What are the two chopsticks? C0 and C1. If P1 wants to eat, then P1 needs, you can see P1 needs C1 chopstick and C2 chopstick. So P1 needs C1 and C2. Similarly, if you take from this diagram P2, if P2 wants to eat, then he needs C2 and C3 chopsticks, and P3 needs C3 and C4, and similarly P4 needs C4 and C0 chopsticks. Now, what is the problem here? So before proceeding with the problem, make a note of this one, all of you. By seeing this scenario, you already know, like, each philosopher each philosopher must require two chopsticks to eat the rice. This is the basic requirement. Okay, what are the two chopsticks? One from the left and one from the right. So this is the condition that is required. Okay, now if this is the condition, what will happen? What are the problems that will acquire? Obviously, if P naught wants to eat the rice, the philosopher needs P naught needs C naught and C1, and P1 needs C1 and C2, right? But if this is the scenario, what are all the problems that may arise? Let us highlight those problems. The problems that may arise are, first problem is, suppose uh, here if P naught, understand this scenario, if P naught wants to eat, okay, now if P naught wants to eat, then what happens? P naught will capture the C naught and C1, isn't it or not? If P naught wants to eat, if P naught wants to eat, P naught will capture C naught and C1. Now if P1 also wants to eat at the same time, can P1 wants to eat, can he get C1? No. Why? Because C1 C1 has been already taken by P naught. This P1 can't use this chopstick of C1, right? So P1 is not getting the C1, but P1 is getting C2. But because he didn't get the other chopstick C1, he can't eat. Similarly, when P naught is having his food, if P4 wants to eat, P4 what he wants, he needs C naught and C4 chopsticks. But P4, if you see C naught is already in the control of P naught. So P4 is not able to get this C naught chopsticks, but he can get the chopstick of C4. But even though he got the chopstick of C4, he cannot eat. Why? Because the other chopstick is not available. From this scenario, what you understand is, if one philosopher is eating, that is in our case P naught, his adjacent philosophers are not able to eat simultaneously. Isn't it or not? If P naught is eating, then P1 and P4 cannot eat simultaneously when P naught is eating. Why? Because the chopsticks C naught and C1 are already under the control of P naught. But if P naught is eating, P3 can perform its eating. Why? Because P3 P3 needs what chopsticks? P3 needs C4, which is available, and C3, which is also available. Right? Or P4 can eat. If P naught is eating, at that time P4 can also eat. What is that? So not P4, what is that? P2 can also eat. P2, what is it requires? C2 chopstick, which is free, and C3 chopstick. So from this scenario, what you need to understand is, if P naught is performing the task, in that case, these P4 and P1 cannot eat the food, but these two adjacent philosophers cannot eat, but the alternate philosophers, either P3 or P2, is allowed to eat the food. Right. So that is the first problem. So make a note of this first problem also. Adjacent philosophers cannot eat simultaneously. Right? So let us go to the second problem. Second problem is, suppose all got hungry at the same time. Okay, let us take that scenario and understand. Earlier case, P naught got hungry first, so P naught took these two chopsticks. While P naught is eating, then P1 got hungry and P4 got hungry. They could not able to eat. But if P2 or P3, one of them got hungry, they can finish their lunch or they can finish their eating process, right? But the second scenario is, if all the philosophers are hungry at the same time, then in that case what happens? Understand the scenario. P naught. Obviously, the requirement is first they will take the left chopstick and then they will take the right chopstick and they will start the eating, right? Suppose if P naught and all five philosophers got hungry, then P naught what it does? It will take P naught, P1, all got hungry. So P naught, P1, P2, P3, P4, all got hungry. So first they will start taking the left chopstick. What is the left chopstick for P naught? The left chopsticks for P naught is C naught. So C naught is under the control, is captured by P naught. C1 chopstick is taken by P1. C2 chopstick is taken by P2. C3 chopstick is taken by P3 and C4 chopstick is taken by P4. Okay. Now after taking the left chopstick, all are now ready to take the right chopstick. Now P naught, what is the right chopstick for P naught? C1, but it is not available. So P naught can't eat, and P1 it requires C2 but it is not available, so it can't eat. P2 requires C3 which is not available, again it can't eat. And C4 is required by P3 which is not available, and similarly C0 is required by P4 which is not available. So with this scenario what you'll understand is, none of the philosopher is able to start eating process. If all are feeling hungry at the same time and all capture their left chopstick, and because the right chopstick is not available, none of them can start eating, and all the philosophers are in starvation. This problem is called as a deadlock problem. So all the philosophers are not able to eat, so they will be led to death, and this problem is called as a deadlock problem. So this is the second problem. So what is the second problem? Make a note of that second problem, all of you. If all philosophers cannot eat, sorry, if all philosophers got hungry at the same time, then this may lead to deadlock. Deadlock means starvation by all the philosophers. So this is the problem that may occur. Right. Now, so considering these things and whatever we have learned till now, there is a basic solution given where if a philosopher wants to eat, what are the things to be done in a semaphore way, the solution has been given. Let us understand that solution first, that code snippet, and then we will see how these problems can be solved. Okay. So make a note of that code, all of you. So any philosopher, if a philosopher wants to eat, then that philosopher has to execute this code first. So what is this code? We will see. Okay, what is this code? Suppose we have understood, like we have considered five philosophers. Okay, now if a philosopher P naught wants to eat the food, the philosopher cannot be directly given the eat option. They have to grab the left chopstick and right chopstick, right? So grabbing the left chopstick is done by this wait statement, and grabbing the right chopstick is done by this wait, next wait statement. So these wait statements will help us in grabbing the opposite side chopsticks. Now once the two chopsticks are grabbed, then the philosopher can eat. Now after eating, the chopsticks has to be placed on the table. For that, first signal, the philosopher after eating has to execute the signal statements, where this first signal statement will help us, the philosopher, to to release the left chopstick first, and then right chopstick can be released. So these methods will help the philosopher to release the chopsticks. Okay, so make a note of that one. So these two way methods will help the philosopher to grab the chopsticks, and this signal to methods will help the philosopher to release the chopsticks after eating. Okay, how this is working and how the semaphores has been used here, let us understand. So you can see here the semaphore that is used is chopstick, and it is of array type, right? So they have taken the semaphore which is semaphore which is chopstick. Okay, as per our example, this chopstick is an array of size 5. That means you may have an array of size 5. Okay, so let us consider this is 0th position. This is 1, 2, 0, 1, 2, 3, 4, 5. Okay, so this is the 0th position. And this is first position, this is second position, this is third position, and this is fourth position. Here, remember the semaphore that has been used here is binary semaphore. Binary semaphore is nothing but the semaphore value can be either 0 or it can be 1. So this is for the chopstick. For our simplicity, I will represent that one as CS. Okay, so initial values of each stop chopstick is 1. What do you mean by 1 is, if a chopstick value is 1, it means the chopstick is free. It has not been used by anyone. If the chopstick value is 1 means it is free. If it is 0 means it has been already assigned to someone. Already assigned to another philosopher. Okay, so let us understand the flow of this one. Whether a philosopher, if they want to eat, whether they could able to execute these two and they could able to get the chopsticks or not. Let us trace this program and understand. Suppose let us consider if the philosopher P naught wants to perform the eating operation, and P naught he is hungry. Okay, so let us consider P naught wants to eat. So first P naught has started its task. So it can't directly eat. So it has to execute the first statement. What is that? Weight of chopstick of, it is 0th process. So chopstick of 0. You already know in our last class, weight operation, what is it does? It will check the semaphore value. If the for your understanding, I'll write here for weight. If the semaphore value is less than or equal to 0, then less than or equal to 0, then what it does? It does nothing. But if it is greater than 0, then it will increment that it will decrement that semaphore value, right? But signal what is does, it will not do any condition checking, it will just increment the semaphore value, right? Okay, now come back to this one. Process P naught, weight of chopstick will be done. weight of chopstick of 0. That means this one. Weight of chopstick of this one. So now what happens? This value is 1. 1 is less than or equal to 0 is false. So what happens? This value will be decremented by 1. So you will get now a value of 0. After this, it will come back here and it will execute weight of chopstick of I plus 1. What is I plus 1? 0 plus 1. Philosopher 0 plus 1 modulus of 5. 0 plus 1 modulus of 5 is 1. That means chopstick of 1. Chopstick of 1 weight value we are executing. So 1 value will be sent. 1 is less than or equal to 0 is false. So it will decrement that value and this value will be now changed to 0. Right. Once these two statements are done, P naught is now performing the operation of eating. Got it? Now P naught, while performing the eating operation, let us consider P1 wants to perform the eat operation. But P1 should not be allowed to enter into eating this one. Why? Because it has to get both the chopsticks, isn't it or not? Whether it could able to grab both the chopsticks or not, let us see. Now P1 will start executing the first one. What is that? Weight of chopstick of I value here it is 1. Chopstick of 1. What is chopstick of 1? It is 0. 0 weight means 0 is less than or equal to 0 is true, which is nothing but it will be in the same condition. So P naught will be P1 will be continuously in this place only. So it cannot come out of this loop until and unless its value is 1. So it will be blocked here. So successfully we could able to block the P1. Got it? And that is what we have done. Adjacent philosophers cannot eat simultaneously. Suppose, let us consider P2 wants to eat. Whether P2 is allowed to enter and eat or not, we will see. P2 wants to eat. So P2 will come here. What is that one? Weight of chopstick of 2. Weight of chopstick of 2 is what? 1. 1 is less than or equal to 0, which is false. So it will decrement this value to 0 and it will come to this place. Weight of chopstick of 2 plus 1, which is 3. Modulus of 5 is 3. So this is 3 chopstick value 1. So weight means it will decrement the value of 1 and then P2 can enter into this critical section. This is our critical section and P2 can also perform this operation. But while P2 is eating, P3 cannot be allowed. Why? Because adjacent philosophers cannot eat this one. Got it? So this we could able to achieve. So when P0 is in the eating option, P1 has been blocked, but P2 is allowed. Got it? But and here once P0 has completed its task, let us consider P0 has completed its task. Then what it has to do? It has to go here and it has to perform signal of chopstick of 0. P0 process. So signal means what? It has to increment this value. What is chopstick of 0? It is 0. It has to increment this value. That is what the signal operation. That means it is releasing the chopstick 0. That means it is releasing C0. Okay. Then it will come here and it will execute this statement. Signal of chopstick of 0 plus 1 is 1. Modulus of 5 which is 1. So it will increment this value. That means this chopstick has been also released. Once it is released, the process P1 which has been blocked here can get that chopstick and it can go to the next statement. Got it? So this is how P0 and P2, the synchronization is happening where we have used the binary semaphores. Got it? And one more thing here, why we are doing the modulus operation? Because after C4, you should not go to C5 because C5 is not existing. It has to go to C0 where a circular queue operation has to be done. That's why a modulus of 5 has been done. Right? But here, when P0 is hungry, and if it has successfully captured these two statements, these two chopsticks, and when it has entered into the critical section of eating, then we are blocking P1 and we are allowing P2. But this is giving a exact correct solution. But we have got the second problem. What is the second problem? Deadlock may occur. What is the scenario of deadlock is if all philosophers got hungry at the same time. Here P0 could able to capture these two, then P1 felt hungry. But if all got hungry at the same time, then what happens? Let us see that scenario. Suppose all got hungry. P0, P1, P2, P3, all got hungry. P3, P4, all got hungry means all will be executing this first step simultaneously. So P0 will execute weight of chopstick of 0. What happens? I will have that array once again. Okay. So this is 0, 1, 2. So 0, 1, 2, 3, 4. Okay. So initial values are 1. Okay. Now P naught of chopstick of 0 will be made to 0. And P1 of chopstick of 1 will be made to 0. And P2 of chopstick of this one also made to 0. And this one also made to 0. And this one also made to 0. Now P naught will come and execute this statement. What is that? Chopstick of 0 plus 1, which is 1 modulus of 5 is 1. Chopstick of 1 is what? 0. Because it is 0, it will be in the blocked state. So P1 will be blocked. Now P1 will P0 will be blocked. Now P1 will come. 1 plus 1 modulus of 5 is 2. Chopstick of 2 is what? 0, which is true. So it will also be blocked. Similar goes for P2, P3, P4. All will be blocked and none of the process could able to come to the critical section, which leads to our problem, which is our deadlock problem. Got it? So this problem could not able to solve this deadlock problem if all processes wants to eat or got hungry at the same time. Okay, now what are all the solutions they have suggested for avoiding this problem? So the solutions are approaches they have suggested. Make a note of these three approaches. Three approaches. What are the three approaches are? First approach is, instead of having 5 philosophers at one time, have 4 philosophers only with 5 chopsticks. Then it may resolve the problem of deadlock. Instead of having 5 philosophers and 5 chopsticks, have a scenario where 4 philosophers and 5 chopsticks are used. Then the problem of deadlock can be erased. Okay. Second scenario. The second scenario is given like, a philosopher will be allowed to eat only when both the chopsticks are available. Okay. Observe here the case, if P naught, this case. Okay. What happened this case? If P naught captured this chopstick and it has been blocked here because it didn't get that chopstick. In that case, if it is not getting the right chopstick and it is holding the left chopstick, then the solution given is, if you are not able to get the second chopstick, release the chopstick that you have already captured. That may help in resolving this deadlock. Got it? So the scenario here is, release the other chopstick if you could not get the release the first chopstick that you are holding if you could not get the other chopstick. In the other words, you can say eat when only both the chopsticks are available. Otherwise, release the chopstick that you already grabbed. Right. If you got one chopstick and if you could not get the other chopstick, then release the chopstick that you have already grabbed. This may help us in resolving the deadlock. Third approach they have suggested is, change the order to avoid the deadlock. Change the order of grabbing the chopsticks. Till now, we have understood like a philosopher has to grab the left chopstick first and then the right chopstick, right? But change the order, like odd person will be grabbing in the other way and even philosophers will be grabbing in the other way. Way it is mentioned like this, change the order like this. Odd philosophers. What are all the odd philosophers? 0, oh, sorry, 1 and 3. Odd philosophers should grab left first and then grab right. And even philosophers has to grab the right chopstick first and then the left chopstick. So if you change the order, not all philosophers will be grabbing the left chopstick first and then the right. If you change the chopstick grabbing order by the odd philosophers and even philosophers positions, then that will also help us in changing the deadlock. So these are the uh, approaches that has been suggested to avoid the second problem, that is our deadlock problem. So this is how a solution to this dining philosophers problem has been given using semaphores. I hope you all are clear with this approach. Let us all meet in the next lecture. Until then, thank you all of you.